Intrinsic concentration. In the previous lecture, we have seen that Fermi energy level coincides with intrinsic energy level in case of intrinsic semiconductor. Here we will derive the expression for intrinsic concentration, which depends on energy gap. As we know, the concentration of electrons in conduction band is Nc e to the power n is Nc e to the power minus Ec minus Ef by Kt. For intrinsic semiconductor, N is Ni, that is Nc e to the power Ec minus Ef, because Ef is Ei in case of intrinsic semiconductor. And concentration of holes, that is P, in valence band is Nv e to the power minus Ef minus Ev by Kt. In case of intrinsic semiconductor, concentration of holes is equal to intrinsic concentration. So Ni is Nv e to the power minus of Ei minus Ev by Kt. Again, Ef is replaced by Ev because in intrinsic semiconductor Ef is Ei. Now, equating equation 1 and 2, so we have Nc e to the power minus Ef minus Ei by Kt, that is equal to Nv e to the power minus Ei minus Ev by Kt. Okay, instead of equating the two equations, we will take the product of two equations. Taking the product of product of 1 and 2. So left hand side is Ni square, in right hand side we have Nc Nv e raised to minus Ec minus Ei plus Ei minus Ev by Kt. So Ni square is Nc into Nv e to the power minus of EC minus EV by KT. So this Ni square EC minus EV is nothing but EG, forbidden energy gap. EG by KT. Now we can replace the expression for NC and NV in the previous lecture. We have seen that we have seen the expression for NC and NV. NV is gamma root pi by 2 KT to the power 3 by 2, and similarly we have expression for NC also. Okay, so now replacing NC and NV. NC is gamma root pi by 2 KT to the power 3 by 2. Similarly, NV is also gamma root pi by 2 into KT to the power 3 by 2 into e to the power minus EG by KT. So Ni square is gamma square pi by 4 KT to the power 3 e to the power minus EG by KT. Now gamma is constant and pi by 4 is constant. K is Boltzmann constant, which is also constant. So gamma square pi by 4 into K to the power 3 is equal to A naught, which is equal to Avogadro number, and we are left with T cube e to the power minus EG by KT. So this is the expression for intrinsic concentration, which depends on temperature and forbidden energy gap. Now let us see the position of Fermi level in N-type semiconductor. Fermi level in N-type semiconductor. We have the expression for concentration of electrons in conduction band, that is NC e to the power minus EC minus EF by KT. In N-type semiconductor, concentration of electrons is equal to donor impurity concentration. So this ND is NC e to the power EC minus EF by KT, or natural log of Nd by Nc is minus of Ec minus Ef, Ec minus Ef by Kt, or Ef Fermi energy level is Ec plus Kt natural log of Nd by Nc. This is the expression for Fermi energy level in N-type semiconductor. Now, if semiconductor is lightly doped, in that case Nd is less than Nc, or Nd by Nc is less than 1. So the natural log of Nd by Nc is negative. So if natural log of Nd by Nc is negative, then this will give Ef less than Ec, which means if semiconductor is lightly doped, N-type semiconductor is lightly doped, then Fermi energy level is below the conduction band. This is conduction band, valence band, lowest energy of conduction band Ec, highest energy of valence band Ev. At the center we have intrinsic energy level. Ef is less than Ec, it means Fermi energy level lies below the conduction band. This is the position of Fermi energy level in lightly doped N-type semiconductor. Now if semiconductor is heavily doped, if semiconductor is heavily doped, then Nd is greater than Nc, or Nd by Nc is greater than 1, which means natural log of Nd by Nc is positive. So this will make Ef greater than Ec. So in heavily doped semiconductor, N-type semiconductor, Fermi energy level lies within the conduction band. This is the position of Fermi energy level in case of heavily doped N-type semiconductor. Now let's see the position of Fermi energy level in P-type semiconductor. Fermi level sorry, in p-type semiconductor. Now we have the expression for concentration of holes in valence band, that is Nv e to the power minus Ef minus Ev by kT. In p-type semiconductor, concentration of holes is equal to acceptor impurity concentration. So this Na is Nv e to the power Ef minus Ev by kT. So natural log of Na by Nv is minus of Ef minus Ev by kT. So Ef is now kT into natural log of Na by Nv this is Nv natural log of Ef this is minus plus Ev. This is the expression for Fermi energy level. Now if semiconductor is lightly doped, for lightly doped semiconductor, Na is less than Nv, so Na by Nv is less than 1, or natural log of Na by Nv is negative. So negative in the expression for Ef, minus minus becomes plus. So Ef is now greater than Ev. So if p-type semiconductor is lightly doped, then Fermi energy level lies above the valence band. This is the position of Fermi energy level in case of lightly doped p-type semiconductor. Now if semiconductor is heavily doped, if p-type semiconductor is heavily doped, in case of heavily doped semiconductor, acceptor impurity concentration is large as compared to Nv. So this Na by Nv is greater than 1, or natural log of Na by Nv is positive. So this will make Ef less than Ev. Sorry. EF less than EV. So if semiconductor is heavily doped, then Fermi energy level lies within the valence band. This is the position of Fermi energy level in case of p-type semiconductor. Now let us see the electrostatic potential of n-type semiconductor. In n-type semiconductor, the expression for concentration of electrons is Nc e to the power minus Ec minus Ef by Kt. Now, if we add and subtract EI here, then we can express the entire expression in terms of Ni. This N is Nc e to the power minus of Ec minus Ei by Kt into e to the power minus of Ei minus minus Ei Ec minus Ei okay, Ei minus Ef by Kt. Now this Nc into e to the power minus Ec minus Ei by Kt is Ni. So the expression for concentration of electrons in terms of Ni and Ei is N, that is Ni e to the power minus Ei minus Ef by Kt. Now, in n-type semiconductor, concentration of holes is donor impurity concentration. So this Nd is Ni e to the power minus of Ei minus Ef by Kt. So Nd by Ni is in fact natural log of Nd by Ni is minus of Ei minus EF by KT. So this is EF minus EI EF minus EI is KT ln ND by NI, and this is phi n. Electrostatic potential of n-type semiconductor in electron volts. Now, if we have to write this potential in volts, then this is phi n by Q or KT by Q ln ND by NI. This is the expression for electrostatic potential of n-type semiconductor in volts. This is the position of Fermi energy level in case of lightly doped n-type semiconductor, and this gap is electrostatic potential of n-type semiconductor, phi n. Similarly, we can derive the expression for electrostatic potential of p-type semiconductor. Electrostatic potential of p-type semiconductor. Now, the expression for concentration of holes is NV e to the power EF minus EV by KT. Now again, we have to express this expression in terms of Ni and Ei. So adding and subtracting Ei here. Now we will break this expression. E to the power minus of EF minus EI by KT, and e to the power minus of EI minus EV by KT. Now this NV into e to the power minus of EF minus EI by KT is Ni, intrinsic concentration. So the expression for concentration of holes in valence band in terms of intrinsic concentration and intrinsic energy level is Ni e to the power minus EI minus EV by KT. Now in p-type semiconductor, concentration of holes is equal to acceptor impurity concentration, and Na is Ni e to the power minus of Ei minus Ev okay. We have to express there is something mistake okay, let me correct. Ef minus Ei, Ef minus Ei, Ef minus Ei, Ef minus Ei, okay. Actually, this is Ni. So the expression for concentration of holes is P into Ni. P is Ni e to the power minus of Ef minus Ei by Kt. In p-type semiconductor, concentration of holes is acceptor impurity concentration. So Na is Ni e to the power Ef minus Ei, Ef minus Ei, sorry, by Kt. So natural log of Na by Ni is minus of natural log of Na by Ni is minus of Ei minus minus of Ef minus Ei by Kt. So this Ei minus Ef is Kt natural log of Na by Ni, and this Ei minus Ef is phi p, that is Kt ln Na by Ni, which is electrostatic potential of p-type semiconductor in terms of electron volts. Now we can write this expression. If we have to write this electrostatic potential in volts, then this is Vn, that is it is Vp, that is phi p by q, that is Kt by q natural log of Na by Ni. This is the electrostatic potential for p-type semiconductor in volts. This is the conduction band and valence band. The position of Fermi energy level for lightly doped p-type semiconductor is Ef. So this difference is phi p, electrostatic potential for p-type semiconductor. Now we can draw the energy band diagram for PN junction, and with the help of electrostatic potential of N-type semiconductor and P-type semiconductor, we can derive the expression for barrier potential for PN junction. Band diagram for PN junction under zero bias. Let us assume there exists a depletion region. Now, Fermi energy level for P-type semiconductor and N-type semiconductor is uniform throughout the PN N-type semiconductor. This is the position of Fermi energy level in N-type semiconductor, and this one is for P-type semiconductor. Now the valence band in P-type semiconductor, this is the position of EV, and this is intrinsic energy level in P-type semiconductor, and this one is the conduction band for P-type semiconductor. The gap between EC and EV is EG, and this is half of EG. This gap is 1/2 EG. This is the position of conduction band in N-type semiconductor. Intrinsic energy level is here, and this is EVN. Now the electrostatic potential for N-type semiconductor, this is phi n, EFN minus EI, and for P-type semiconductor, this is phi p. So this summation of these two is phi naught. Phi naught. And phi naught is phi naught is phi n plus phi p. Substituting the expression for phi n and phi p, this is kt ln nd by ni plus kt ln na by ni. So the expression for phi naught is kt ln NAND by Ni square. This is the expression for barrier potential in electron volts. Barrier or built-in potential. And in volts, this is kt by q natural log of Na by Nd divided by Ni square. This is the expression in volts. Now in this diagram, this gap, the gap between conduction bands of p type and n type is also phi naught, and the gap between valence band of p type and n type is also phi naught under zero bias.